Let's start. So welcome to the Wednesday morning session. We will start with Nima online, talking about the positive geometry in cosmology. And just a reminder, if you have a question, please raise your hand. We will get to you with microphone. Otherwise, Nima cannot hear the question. Okay, so please, Nima, take it.
All right, that's great to be with you guys again. So this is the second lecture. Just as a reminder, our purpose in the first lecture was really to introduce the object of study, which is the wave function in flat space, and also for simple toy models of conformally coupled scalars in FRW cosmology, very closely related wave function in cosmology. Actually, we spent almost all of our time talking about the wave function in flat space for a single graph. So today we'll begin just by finishing the story, talking about the wave function in cosmology for these toy models of a conformally coupled scalar in FRW cosmology. And we'll talk about how we go about thinking about summing over all of the graphs first. But that's really just to finish the introduction to the object of study. And in the second part, we're going to talk about this move from geometries that capture all the Feynman diagrams together in a single object, the story of the Associahedron, and the ABHY realization of the Associahedron that Yara just told me Alok has spoken about at the school. We'll talk about what the move is that takes us from that picture to doing the analogous thing for the wave function. And as we'll see, the essential sort of combinatorial idea behind it, or the thing that needs to be done, is very, very clear once we understand this this way of thinking about what the sum over all graphs for the wave function represents. And while the story for amplitudes is really all about non-overlapping chords, triangulations that are things that are associated with non-overlapping chords, we will see that the way to think about the wave function is to replace the notion of non-overlapping chord with non-overlapping subpolygons. So they're sort of very closely related objects. They're not in sort of radically different worlds. And this is going to give us but pursuing this way of thinking will sort of lead us naturally to start with the Associahedra and, in a literal sense, blow them up or shave them off to go from Associahedra to these Cosmohedra. I think, as you'll see, that the essential sort of combinatorial ideas here are very simple, and these objects are, it seems, are likely to show up in many settings. In any setting where you have the sum of a bunch of diagrams, but each diagram has an extra structure associated to it. Such an object is likely going to show up in some guys, and I hope you can you'll appreciate the sense in which that's something that's going to be good to look for. Okay, so again, just as a reminder of where we're going, you've probably seen pictures like this in Alok's lecture. This is for the case of n equals 6 particle scattering. It's the Associahedron that captures all the Feynman diagrams together in a single object, and all the sort of partial triangulations of a polygon, or all possible partial factorizations of an amplitude in faces of different dimensionality. And the object on the right is going to be the Cosmohedron, which, if you sort of squint, and we'll see this much more precisely, is really obtained by starting from the Associahedron and blowing up all of the faces in a very particular way. So you get this much richer object, but it's very closely related, and all of the facet structure of all the faces of the Cosmohedron are now going to be about non-overlapping subpolygons, this Russian doll structure of non-overlapping subpolygons, rather than simply non-overlapping chord. So hopefully you'll get a better understanding of what this picture means as we proceed. But let's go back and finish the story. So remember, we had for a single graph, we already had, well, first let me just, before getting to a single graph, what are we talking about? We're imagining that just to begin with in flat space, we're calculating the wave function for just like, so we have a theory of, let's say, a scalar field. It doesn't even matter if it's colored or not here, but just kind of a generic theory. But we're calculating the wave functional, which we can imagine. So this is at some fixed time. So I call the time eta. So it's like the conformal time in cosmology as well, but it's eta equals 0. So we're looking at the vacuum state. We can think of this as being obtained by computing the path integral over all field configurations that end on phi at here at eta equals 0, with the I epsilon prescription going back off to minus infinity. So that's the path integral way of evaluating the wave function. You could also solve the Schrodinger equation, like undergraduate quantum mechanics, to determine the vacuum wave function. There's lots of ways of doing it. But this is something that starts off life. It's natural to work in momentum space because I have translational invariance on the eta equals 0 surface. So it starts off life as the Gaussian piece, which is just what you get for each individual harmonic oscillator. There's some DDK here. But then there is a cubic term, which we'll just call psi3. Which has a delta function for spatial momentum conservation times phi of k1, phi k2, phi k3. And then there's a psi4. This is all in the exponential, right? Always the delta function for momentum conservation, phi k1 through phi k4, and so on, okay? So it's these psi's that we're going to compute, these wave function coefficients that are the things that we're going to compute. And these wave function coefficients are calculated by Feynman diagrams. So if you want the contribution to like psi sub n, then you just draw all the Feynman diagrams where you imagine lines coming out where everything is anchored to this boundary at eta equals 0. And we can have loops, we can have all the usual stuff. But the point is that in these diagrams, and here's eta equals 0, we have two kinds of propagator. From a time eta, we have the sort of bulk to boundary propagator that depends on the energy, or when I say energy, I always mean by the magnitude of the spatial momentum of k and eta, which is just e to the I k eta. And then also there's a bulk-to-bulk propagator that depends on sort of k and eta 1 and eta 2, which is the Feynman propagator, but minus this correction, e to the I k eta 1 plus eta 2, that's 1 over 2 magnitude of k, which is there to ensure the boundary condition that phi is fixed at eta equals 0. Okay, so it's just normal Feynman diagrams with these Feynman rules, and we integrate all the times. All the times are integrated from minus infinity to 0. Okay, so that's the computation, the way you do it from the path integral. But as we discussed, we can derive an alternate way of capturing the answer, which is, in an invariant sense, is more physical. And the invariant sense in which it's more physical is that this bulk path integral picture, every term in the perturbation expansion, every term you get from expanding the bulk-to-bulk propagators in particular, have unphysical singularities that come from this sort of artificial breaking up of the time into the different time orderings. And those singularities just cancel in the final sum. But there's another way of expressing the answer where every single term has singularities that are legal, have correct singularities, no spurious singularities that occur in the answer. And that's this what we call this tubing picture. So you draw your diagram, but what you do is you surround it with these tubes, non-overlapping sets of subgraphs, and as many of them as you can. Okay, so in this case of the 5-point problem, again, I have spatial momentum conservation, so everything is on the support of spatial momentum conservation. But every term is just given by, so you look at any tube, and associated with any tube, you write down 1 over the sum of all of the energies of the lines that enter the tube. So for example, from this biggest tube, we would have just 1 over the sum of all of the magnitude of k's. That's what we called the total energy pole last time, and that has an important significance we'll come back to in a moment. But what we have, I'll remind you of in the moment, but for example, with this tube, we have the factor 1 over K1 plus K2 plus this momentum, right? That momentum here, which could be sorry, we have 1 over we have K1 plus K2 plus K3. But we have this momentum coming from the outside, which can be thought of as like K4 plus K5, the magnitude of K4 plus K5. Okay, so there's a factor like this, which is just the sum of all the energies entering a tube. And you just multiply them all together, and then you sum over all the tubings of the graph. Okay, so that's the key essential difference between the diagrammatic expansion for an amplitude and for a wave function is for such a simple theory as the scalar theory. There's no numerator factors for the amplitude; is just one of the product of propagators. But for the wave function, you draw the graph, and that's where the adventure begins. Okay, so after you draw the graph, there's still the sum over all the tubings. And as n becomes large, as a number of as a graph becomes large, actually the number of tubings grows factorially. Okay, so it's really quite a bit more complicated than an amplitude. Okay, now for obvious reasons, we call this a Russian doll structure. Yes.
Hi. So the question is the following. It's a slightly broader question.
Yes.
Perhaps you addressed this last time, but I wasn't there. If you could do the same thing for ADS correlators, and
yes,
then
it's identical. There's yeah, exactly.
Right. But there's one difference, which is I think in the cosmological context, the real observables are when you square the wave function and you integrate over.
Yes, that's right.
The reason this might be the thing that's confusing me is that if you consider the case where there were UV divergences in the theory, then you would expect that the observables are UV safe quantities that you're computing. But you might find that there might be cutoff dependent terms in the wave function itself. Is this something one should worry about? That the wave function itself might have terms that are proportional to the cutoff, which are counter terms, and you need those terms so that the final correlators you get by squaring the wave functions and integrating do not have a cutoff.
I think this does not occur in practice. And one, what does very often occur is that there are phases, of course. So there are often like as in ADS. I mean there are divergences as you go near the boundary that you interpret as local counterterms in the CFT, right?
Yes.
So we have exactly the same thing here. Of course, we have things that, but those are not objects that have interesting singularities. So there are also things that are removable by field redefinition, local and so on. So they're not things that have these interesting 1 over k type.
Right. Yeah. That's certainly the case. But if you those things which would be analytic in 2 of the momenta, so that they're local. Once you square the wave function and integrated it, they might stop being analytic. So they might contribute to the observable cosmological correlator.
Yes.
And so is that something we should worry about, that we have to keep track of these terms?
I mean, definitely in principle, the only thing that we really care about are the actual correlators. So that's for sure. Today, we're mostly going to be concerned just with the structure of the perturbation theory. And actually, the structure of the perturbation theory for the correlator is very closely related to that of the wave function. So it's but yes, in principle, those things can happen. Actually, I mean, one of the hardest things to deal with in this, and this is one of the reasons this didn't become, apart. I mean, you can ask this, for example, this tubing picture is in some sense easier and invariantly sort of better than the Feynman diagram picture, than the path integral picture for calculating the wave function. So you know, what gives? You know, why did everyone switch to Feynman diagrams? Okay, well, so Feynman diagrams are a little bit easier for amplitudes, but more invariantly, it's things like implementing Lorentz invariant cutoffs are much trickier when you do it in this language. It's not manifestly Lorentz invariant. Then now, if you did it with a physical, you know, as usual, if you do it with like completely physical bulk theory, or even something, you know, Pauli-Villars or something, but something which is not a hard momentum cutoff, some physical thing in the bulk. If you do it consistently, everything should work. But of course, it's much easier to do that in a manifestly Lorentz invariant picture than in something like this. So I think those issues about the UV divergences are more serious when you deal with the with computations in the language of the wave function.
Okay. Okay. Thank you.
All right. Okay. So that's a picture for a single diagram. We look at all the tubings. We multiply this factor one of all the energies coming into the tubings, and that's it. That's as opposed to the amplitude, where we just multiply one over all the Lorentz invariant propagators. Now, the other thing that I mentioned last time is this discovery of Suvrat, who was just speaking. That when you live on this pole, every one of these diagrams, there's always the biggest tube that contains everything. And if you live on the locus where the sum of all of these energies goes to zero, of course, these magnitudes are really magnitudes. So they're really sort of positive numbers. So if so in the physical region, they're all positive. You can't access this. But if you imagine this is an analytic function of all these quote unquote energies, which are the magnitudes of the k's, and you just analytically continue some of them to be positive and some of them to be negative, then you can go to the locus where this thing goes to zero, and the coefficient of that, the residue on that locus, turns out to be the scattering amplitude. Okay, so that's a very beautiful thing, and as I stressed, the sort of data for the wave function and the data for an amplitude are very, very similar, because we have momentum conservation. In both cases, I would draw sort of a polygon with all the momenta adding up to zero. It's just that for the amplitude, we also say that all the corresponding energies add up to zero. Okay, and we allow some of them to be positive and some of them to be negative to correspond to in and outgoing states. So the data, the kinematical data that labels the wave function is exactly one variable more than that which labels the amplitude, namely the sum of all these energies. And so when I go on the locus where the sum of all the energies is zero, the coefficient of the pole actually turns into the amplitude. Okay. All right. Now, before we move on to talking about summing, the sort of picture for summing overall graphs, let me say something about cosmology, or at least the sort of toy model that we're talking about. So we're going to talk about just in flat space a model which is let's say d phi squared, but I have some general time-dependent coupling for the phi cube term. Okay, and of course it doesn't matter if it's phi cube, but let's just do this as an example. Now, why is this a toy model for cosmology? Well, it's very easy to see that if you're working in an FRW cosmology, and in FRW cosmology, I can always sort of write the metric by scaling out some overall conformal factor A of eta So this is what the metric looks like. But if in this cosmology I have a conformally coupled scalar field, so the Lagrangian, at free level, a conformally coupled scalar field. So the Lagrangian would be a half g mu nu d mu phi d nu phi, and there's some constant. I don't remember if it's a sixth or a 12th, but anyway, there's some specific constant phi squared coupled to the Ricci scalar. With the special choice of a coupling, a special choice of coupling is made such that by performing a Weyl transformation, you can completely get rid of the time dependence in the free kinetic terms. Okay, so that's what the conformally coupled means. That if I just write phi equals a of eta, some sort of phi hat, then the Lagrangian in phi hat variables just turns into just the usual d phi hat squared. Okay, in this case, just the massless d phi hat squared. So the free part is conformally coupled, but the interactions don't have to be conformal. And so, if in this theory I have a time-independent interaction, after I do the conformal transformation, I get a time-dependent, eta-dependent interaction here. Okay, and if a of eta goes like a power of eta, for example, if this power is equal to -1, we have de Sitter. Different choices of power give me matter, radiation, etc. If it's -1 plus epsilon, it's a good proxy for slow roll inflation. Then that turns into a similar power law behavior for g of eta. So g of eta also goes like eta to a power. Okay. Okay, so if we learn how to deal with this flat space wave function with this time-dependent coupling, then we're also doing conformally coupled scalar in FRW cosmology. So it's really the very, very first simplest example of cosmology you could talk about, which is equivalent to flat space, but with a particular set of time-dependent couplings. Okay. Well, this is very simple to deal with because we can always Fourier represent these couplings. Okay, so let me Fourier represent these g of etas as the integral over some, let me call them d omega, e to the I omega eta times some g tilde of omega. And you see, so let's say we go back to our, if we go back to our 4-point problem. So if I have some eta 1 and eta 2 here, then each one of these vertices now, we have an integral d eta 1, d eta 2. We have, for example, this e to the I k1 plus k2 on the left, eta 1, and the same thing on the right. But now we should put a g tilde, we should put a g of eta 1 here for the time-dependent coupling. But once I Fourier represent this, then I can just bring the d omega out front. And you see, this is exactly the same. It's exactly the same as if I just shift what I mean by the sum of all the energies entering here by omega. Just by Fourier representing, I get k1 plus k2 plus omega. And similarly on the other side. So in order to get this cosmological wave function, all I have to do is compute the flat space wave function, but shift the energies by omega and integrate with respect to the kernel g tilde of omega. Okay, so that's why it's so easy to get the cosmological wave function from the flat space ones. And something we maybe talked about before that's convenient to do when you draw these pictures is sort of make a slightly simpler version of the pictures where all the energies that enter here are replaced by some variable. So we sometimes call them x's for the external ones. So some x1, x2, and x3. And there are the energies associated with the edges are called y. So this would be sort of y1, y2. So in order to get the cosmological wave function as a function of all of the x's and the y's, we just have to integrate d omega G tilde of omega for all of the vertices times the flat space wave function, where the x's are shifted to x plus omega vertex. Okay, so that's the connection between the flat space and the cosmological wave functions. And the special case of power law FRW cosmologies is especially simple. For example, if you're doing de Sitter space, the wave function in de Sitter for this model, again, as a function of the x's and the y's of the edges, is literally the integral 0 to infinity d omega for each vertex times the flat space wave function, where all of the x's are shifted by x plus omega. Okay, and if your scale factor is a of eta is a to the minus 1 plus epsilon, so it's just epsilon departed from a de Sitter, then you just shove in here the product over all the omegas raised to the epsilon. Okay, so this is a very, very simple relationship between the cosmological and the flat space wave functions. Okay, any questions about this before we proceed? No? Okay, so now let's move on to talking about summing over diagrams. Okay, so and let me remind you of something that you saw in Alok's lectures, certainly, that if we're now talking about this trace phi cube theory, so this theory of colored scalars, then it's very useful to think about summing over diagrams as being just individual Feynman diagrams, and an individual Feynman diagram is useful to interpret as being associated with the triangulation of an n-gon. In fact, well, the n-gon to begin with is natural to think about in a way that we've talked about several times already. This is again for amplitudes. We'll have an almost identical picture for the wave function. We have this picture of the momenta adding up to 0 to get this momentum polygon. And then so for example, if I draw this at 4 points, so I'd have this P1, P2, P3, P4. But this picture is also very useful because it usefully records the propagators that enter in the diagrams. For example, if I draw an S-channel diagram, and here it matters that that we have color, so that we've drawn the particles in a color ordering. So there's an ordering for the labels, which is also the ordering that dictates the order in which these arrows are drawn to form the polygon. So if I draw this S-channel process, the momentum that enters here, the propagator is 1 over P1 plus P2 squared. If I draw the T-channel process, it's 1 over P2 plus P3 squared. But these guys are very beautifully represented in the picture. So if I draw 1 over P1 plus P2 squared is like that distance squared in this problem. And 1 over P2 plus P3 squared would be the other diagonal. And so already in this very simple example, we see that summing over the Feynman diagrams is the same as is associated with sort of triangulations of this n-gon. And again, that's not a coincidence because we can draw the dual of this triangulation by putting a point in the middle of every triangle and connecting the points that are that share edges. The dual of the triangulations are precisely the S-channel diagram and the T-channel diagram. Okay, so and so if we just do one more example of this, again, you've seen this in Alok's lectures, I'm sure. But if we take 5 points and I draw this picture, then the dual diagram looks like that. And again, this is a 5-point Feynman diagram, and it tells us exactly what the propagators are, right? So, so this propagator would be 1 over P1 plus P2 squared, and so on. Okay, so okay. So we've already therefore seen that it's useful to think about just diagrams as triangulations of a the n-gon. And so if we associate a variable for general n-gon, there's a variable that we can think of as the length squared between the points I and j. So we call that variable xij. This is also, they're sometimes called the planar variables or planar propagators. So these are the things that show up in the diagrams. We can say that the amplitude is simply the sum over all the triangulations, where for each triangulation, we take the product over all the xij's in the triangulation of 1 over x. Okay, and that's the amplitude for this very simple trace phi cube theory. All right. Now let's try to see what the analog of this is for the wave function. So let's go back even at 4 points. So, at 4 points, we had a sort of a picture like this. That's sort of one diagram. Again, all these legs we're imagining are going up to the eta equals 0 surface that I'm just drawing as a line now. I can have the sort of T-channel diagram that I could draw like this. Okay. Okay, but remember what we're supposed to do with each one of them is draw these tubings, right? So that's the contribution. In this case, only one tubing associated with that one. And here I draw similarly. I have these tubings. Now, I can go back to this picture and just sort of, now I can think that this is now exactly the same picture, except the spatial momenta that are adding up to 0. So I've only drawn the spatial momenta here. Okay, the diagram again, the diagram again is sort of captured here by an S-channel picture and here by a T-channel picture. But now the tubings themselves have a nice interpretation. So you see, the total energy is just that variable. Instead of being a distance squared in this picture, the variables that show up in the wave function are the perimeters, okay? For example, the total energy is the perimeter of the entire thing, of the entire n-gon. This tubing, the energies of this tubing is K1 plus K2 plus K intermediate. Well, who is that here? It's this K1 and K2 plus K intermediate. See, this is the perimeter of this triangle. This other guy is the perimeter of the other triangle. Okay, okay, so similarly, I have the same things on the other side. And so, what does the picture look like? The picture looks like instead of having instead of just drawing a chord and being done with it, I'm filling the inside of the n-gon with non-overlapping subpolygons. And for every subpolygon, I multiply by a factor. That's the 1 over the perimeter of that subpolygon. So let's look at a slightly let's look at a 5-point example. So when we had this guy, so remember here there was now, even for this one diagram, there were two tubings. So let's see if we can interpret those two tubings in our picture again. So here's one of them. Okay, so here the corresponding picture would be a pentagon. Okay, so this is 1, 2, 3, 4, 5. Okay, we'd have something like this: 1, 2, 3, 4, 5. But now, again, the very biggest tube is the full perimeter of the full thing. But now, what about this guy? That tube surrounds precisely this guy. Okay, so it's this square. The disjoint tube on the other side, this guy here would be, this guy we just drew, this guy would be this triangle on the other side. And then if I look inside this, purple tube, the two, I'll leave them blue ones in here, are again these triangles inside the square. So once again, what I'm doing is not just drawing chords, but I'm filling the polygon. First, there's the entire perimeter of the whole thing, but on top of that, I'm filling it with maximal collection of nested subpolygons, non-overlapping. When we say polygons don't overlap, it means no edges can cross. One of them could be contained inside the other. That's legal. They could be disjoint. That's legal. They can't have edges that cross each other. But in order to get the contribution to the wave function, I have to sum over maximal collections of non-overlapping nested subpolygons. And for every subpolygon, I write down a factor which is 1 over the perimeter of the subpolygon. Okay, so to summarize, the amplitude is a sum over all triangulations, the product of the 1 over these xij's for the xij in the triangulation. The wave function is a sum over all of these, and instead of continuing to say maximal collection of non-overlapping polygons, we'll just call them Russian dolls, okay? All of these Russian dolls, and then we have a product of 1 over the perimeters that are associated with all of the subpolygons that belong to the Russian dolls. Okay. Okay, so that's the and you see it's very striking that they're not so distant from each other, obviously, but that's what we need to somehow wrap our heads around, is think about how to control and understand the sets of all the Russian dolls, not just a set of all the diagrams. And again, you can think of the diagrams themselves as being maximal collections of non-overlapping chords. This is more than that. It's maximal collections of non-overlapping subpolygons or Russian dolls. Okay. Any questions about this? This is maybe another good time to stop and ask if there's questions.
One question.
You still have to sum over the triangulations to get the wave function coefficients, right?
Sorry? Well, yeah. So if you like, I mean, you can just say that you sum over all possible nested collections of subpolygons, and that forces you to sum over all the triangulations. Because any remember, it has to be a maximal collection of subpolygons, so they'll always contain little triangles. Okay? You can always have the little triangles. So indeed, you can organize a sum over all the maximal collections of nested subpolygons. First, by picking a diagram, which tells you what the little triangles are, but then you're not done. Then you've got to find all the ways of sort of, if you want to say it from the bottom up, find all the ways of surrounding the triangles with squares and then pentagons and in all possible ways.
Okay, thank you.
Any other questions?
Seems like no other question.
All right, great. Now, something that you learned from Alok, I think in the time that we have left, I think I can explain the sort of basic combinatorics of the picture easily, and then I'll mention a number of the interesting open questions surrounding these objects. But something that you learned from Alok is about the Associahedron. And let me actually begin first with a sort of purely combinatorial picture of the Associahedron, which is just the observation that we have an object that, I mean, that triangulations are important, partial triangulations are important. So triangulations of the n-gon give us all possible diagrams. Partial triangulations give us all possible sort of factorization channels for the amplitude. And it's a striking fact that there exists a geometric object that captures in its face structure all possible partial triangulations. Okay? And so, if I remind you quickly how it works, if I do this for n equals 4, that's sort of trivial because it's just an interval with an S channel on one side and the T channel on the other side. Already, the case of n equals 5 is a little bit more interesting. And the object looks like a pentagon. Again, completely coincidentally, it looks like a pentagon. But the idea is that every edge here is actually a partial triangulation. For example, this edge can be thought of as that triangulation. And this other edge is going to be another partial triangulation, but the two edges meet is when I get a further refinement and I can have both the chords present together. Okay, so that's the claim about the associahedron. It's an object where the faces are associated with partial triangulations, such that a lower dimensional face is a face of a higher dimensional one if the corresponding triangulation is a refinement of the triangulation of the bigger one. Okay, so for example, in this case, one of the edges associated with this with that chord 1, 3. Maybe this is associated with 1, 4. But this vertex is then associated with the presence of both of them. Okay, this vertex is associated with having both 1, 3 and 1, 4. So the vertex is a complete triangulation in this case, and so on. So we can then draw the picture and complete it as you go along. So this is not trivial. It's not even quite trivial at 5 points, but you probably saw this picture in Alok's talks for what this looks like at 6 points. So this is the 6-point association we've already seen here on the left, and we see it's quite a bit more non-trivial. But every single face is labeled by some partial triangulation. So here's a face has just one chord. So the facets, the codimension 1 things, are just labeled by single chords, single factorization channels. The edges are labeled by having 2 chords, but this guy is an edge of this one and that one, and that's reflected in the fact that the 2 chords that we see on this edge are associated, or just are putting together the chords that we see in this face on the left and that face on the right. Okay, and so the vertices are then associated with 3 chords that are allowed that don't cross each other. 3 chords that don't cross each other give us diagrams. Okay, so those are the individual finite diagrams. It's highly non-trivial that such an object exists. It was discovered by Jim Stasheff in the 1960s. It was not realized that it was actually really a polytope that could be cut out by inequalities. It looked sort of flat like this in general for general n until the 1980s. And anyway, has lots of fascinating properties. Okay, so when I say that, when I say this is the combinatorial associahedron, I mean just at 0th order without even giving any concrete formulas for how to cut it out with inequalities and so on. Without doing anything like that, we can already see that that it's non-trivial that all the combinatorics of triangulations, all the possible partial triangulations are captured by the faces of some object. Okay, and once we know that, there's a lot of things that we can. Once we know that, there's a lot of things that we can do with it. So, of course, in order to really connect it to a physics, we need an embedding of the associahedron in kinematic space. And so here there's the sort of very specific realization of the associahedron that is given by imagining that in the kinematic space, that we now really think of the space of these xij variables that are the planar propagators, that we imagine that we ask for all the x's to be positive, but also that they lie on these particular planes in kinematic space that I won't describe in more detail, but these are the sort of ABHY equations that if we also ask these c's to be positive, cut out the associahedron. So for example, for the case of n equals 5, we don't just get a sort of random pentagon that looks like this. We get a very specific pentagon if we choose one way of cutting it out. So in x13 and x14 space, the pentagon looks something like this, okay, with these very specific sort of parallel sides and so on. Okay, so that's a very specific realization of the Associahedron. Now, one of the features I should have also stressed already in the combinatorial Associahedron is that the sort of crucial physics like factorization of the amplitudes is also something Alok, I'm sure, discussed, that when I sit on a pole and an amplitude factorizes like this, so that's reflects some of the most basic physics of both locality and unitarity, that this is reflected in a beautiful way in the structure of the Associahedron itself, that the boundary of an Associahedron, a face of an Associahedron, is itself given by the direct product of lower Associahedra. So this is a more primitive sort of combinatorial geometric fact about these polytopes that is the backbone of this sort of more refined and detailed fact that amplitudes factorize when you go on poles. Okay, and that fact is made obvious by, this is some sort of a fact about these objects as polytopes that is maybe not super obvious, that you don't might not appreciate or notice at first. But this concrete embedding of the Associahedron, this concrete realization of the Associahedron makes this fact obvious. Okay, so the fact that the Associahedron factorizes into the product of Associahedron on its boundaries is made obvious by this picture. Something more surprising, which is made obvious by this picture, is that these Associahedra are actually, while at large n, where n is the number of particles, there is order n squared faces. That's the number of kinematic variables, roughly the number of dot products, pi dot pj, or the xij. There's roughly n squared variables, but there's an exponential number of diagrams. There's 4 to the n vertices, which is also the number of diagrams. So the Associahedron looks very complicated. It looks like a very, very complicated polytope. But in a concrete sense, it is the sum of very simple pieces. Okay, it's a sum of a small number of literally simplices. So this is the so-called Minkowski sum picture. I'm not sure if Alok talked about this much, but this is another fact so it's obviously Associahedron gives you an object that factorizes. But something more surprising is that the seemingly very complicated object with exponentially many vertices is actually built up out of a sum of a small number of simple pieces. And this fact that you can build the Associahedron out of a small number of simple pieces turns out to be intimately related to a sort of bottom-up way that you can start from this sort of combinatorics of diagrams and particle scattering and discover string amplitudes. So this is maybe something Song might have talked about. Once you learn, the bottom line is once you learn how to embed the Associahedron in kinematic space, so it's sort of very important to find a concrete way of cutting it out with inequalities. And once you do that, many other emergent things start coming out. So, and in particular, the fact that you can build it up out of simple pieces is the sort of avatars purely, almost entirely in the world of combinatorics of the fact that there's string amplitudes related to all of these things. Okay, so what we'd like to do now is talk about what the analog of all these things is for cosmology. Okay, so and again, what we have to learn to think about is this story of Russian dolls. Okay, so I want to begin by talking about just a single graph. Okay, so the sort of combinatorial geometry for a single graph. For a single G. Okay. And here I mentioned it, I think last time, but just a sort of quick historical remark is that back in 2017, we did talk about an object associated with a single graph that computed the wave function. Actually, maybe I should have said something back here already in the standard story of the Associahedron. I didn't mention it explicitly. Again, I assume that Alok talked about this, but the concrete connection with physics, not just the geometry, is that the amplitude is to be thought of as this sort of canonical form of the polytope, which is the Associahedron. So this is a notion that makes sense for any polytope, and more generally for positive geometries. There's a geometric space. It has boundaries of all possible dimension. And then there's this privileged differential form that has the prescribed logarithmic singularities, d-log singularities, on and only on the boundaries of the space. And it's that object and the existence of that object that means that the sort of boundary structure of the polytopes get reflected in singularity structure of the corresponding form, which is exactly the properties that amplitudes are supposed to have. So it's a sort of notion of canonical form that takes you from combinatorics and geometry to functions that reflect the factorization properties of the geometries, which we then interpret as locality and unitarity for amplitude. So that's a sort of the general mantra of this subject has been that there's combinatorics and geometry somehow in kinematic space determines an object that, but the physical quantities are ways of interrogating this object by asking questions like find a form that has singularities on the boundaries of this thing, only on the boundaries of this thing, and then that object will be interpretable as an amplitude. Okay, so
Nima, we have a question here.
Yes.
Yeah, so I had this question that in the amplitude picture, the triangulations were connected to the fact that you started off with the phi cube theory, right? If I
Yes.
did a fourth, I was
Yes.
looking at triangulations and so on. In
Yes,
here,
yes.
if you look at the phi fourth, is it like non-overlapping sub?
That's exactly the same. Here we're talking about triangulations for exactly the same reason. And you could talk about more general theories. And it would be I mean, the story goes through in complete parallel. So if you want a more general theory, then you have to have not just triangulations, but general polyangulations. Okay, you have sort of a little for amplitudes, you'd have triangles. If you have quartic interactions, you'd have squares and so on, right? You know, so you have general polyangulations, and you'd have to build Russian dolls based on general polyangulation. So, for example, there will be some kinds of a Russian doll that you couldn't fill in anymore. So if you had a phi to the 4 term, you'd have to make Russian dolls out of now squares. But some squares you couldn't fill in anymore with the triangles. Okay, those would correspond to the quartic interactions. So that's all. You just have to enrich the story to allow both polyangulations and different kinds of doll in the Russian doll, which can or can't be filled in.
So if you have
Did that answer your question?
If you have phi to the 4th, it would stop at the quadrangulation.
That's right. If you had pure phi to the 4th, it would stop there. Exactly. That's right. But you could have mixed phi to the 4th and phi cubed, say. And so sometimes you could keep filling in the Russian dolls, and some of them you can't. So you just have to allow those different possibilities with different coupling constants.
Thanks.
Any other questions? Okay, so so back in 2017, we found with Benincasa and Posnikoff another class of polytopes associated with single graphs. These were these so-called cosmological polytopes, and the canonical form for this cosmological polytope did indeed give you the wave function for a single graph. Okay, so that was a development we were excited about back then. But back then we could not figure out, and still haven't quite figured out, but how to put those cosmological polytopes together for the different graphs in some sort of bigger object. Okay, that was an obstruction. And one of the things that makes this new story for the Cosmohedra fly is that there's actually a different picture for a geometry associated with a single graph. Okay, so. And so that's the first thing that I want to tell you about, that the combinatorial geometry associated with a single graph is what I want to describe. And this does turn out to be an object that is known to mathematicians. They're known as graph associahedra. In fact, sort of ironically, Alex Posnikov, my friend, and also the guy who came up with many of these things in which we worked on together with the cosmological polytope, was the person who came up with graph associahedra. And so, you know, had we thought a lot harder back in 2017, we might have seen this connection a lot earlier. Part of the obstruction is that our definition of graph associahedron and Posnikov's definition are not quite the same. They're very simply related, but and the actual objects are identical. But our geometry for a graph G would be Posnikov's geometry for a closely related graph G dual somehow. Anyway, so okay, so but this is what the first thing I want to tell you about is how to think about Russian dolls. This is really just how to think about tubings of a single graph and see how the tubings are captured by a diagram. Okay, so let me actually start with a slightly a slightly more complicated example, the n equals 5 example. Okay, so we're going to do this sort of n equals 5 example. Remember, in this case, here were my tubes, right? Here were my tubings. I had 2 tubings. This was one of them, and this was another one. Okay, now the first thing to notice here, and this is going to be true for any graph, but we see it already in this graph, is that it's a little bit wasteful to draw all of these pictures, because every single graph is going to have 2 sets of tubes that are always there, okay? I'm always going to have this total energy tube. That's always going to be present, right? And of course, there's always going to be a tube that corresponds to the little circles that surround every vertex. Why? Because remember, the rules are that we have to draw the maximal collection of nested, non-overlapping things, but it has to be a maximal collection. So whatever I do, at the end of the day, I can always add the little circles around every vertex, and I always have the big one around everything. Okay, so those are there always in every tubing. So because they're always there in every tubing, let's just not draw them. They just are taking up space. Okay, so okay, so if we don't draw them, and let's actually go back and draw our picture here in the more minimal way that we had talked about, where we snip off these things that these external lines. Okay, so I've snipped them off, so I'm drawing the picture like this. So now, what are the sort of 2 tubings that I'm talking about? Well, you know, one of them looks like this guy, and the other one looks like this guy. Okay. Okay, so that's what the geometry, sorry, that's what, in this case, I just have 2 tubings, and of course, they intersect each other. They don't overlap, so they can't occur together. So where have we seen this before? Well, this is a lot like our S&T channel story, and there is, in fact, kind of a one-dimensional geometry that you can associate with this. In fact, it looks a lot like the Associahedron. Okay, so it looks like, except here, instead of drawing an S and a T channel, on this end, I draw this tubing, and on the other end, I draw the other tubing. Okay, so this is a little geometry that's an interval that captures the non-trivial tubings for this graph, for this single graph. Okay. Again, to get the full tubings, I have to go back and add in total energy and add in the little guys surrounding every vertex, but those are universal. Okay, so these are the only ones that sort of change from graph to graph. If I do this exercise for the case of this graph, which is what I would get from the 4-point problem. Okay, if I just take this this graph, in this case, there's nothing left, right? Because everything is all the tubings are either the total one or the 2 surrounding ones. So in this case, the geometry would just be a point. Okay. So let's see what we're getting here. Sorry, let me add some pages. So far we look at the here is the graph, and here's the geometry. The geometry is in this case a point. If I have this graph the geometry looks like an interval, where on this end I have this one tubing, and on this end I have another tubing. All right, let's do another example. Let's do a graph that looks like, a 6-point graph, let's say, something like that. Okay, let's look at this this diagram. So this graph would just be, if I strip off the external lines, it looks something like this. So now this is going to be a little more fun. So let's play with this one for a bit. Okay, so who can I have here? Okay, so well, I can have this tube. Oops. I can have this tube, but see, this tube is compatible with, it can occur with this one. Okay. It can also occur with this one. And those are the only two guys that it can occur with. Okay. If I go on, this tube can occur with this big one, or it can occur with this other big one. And those are the only two guys it can occur with. So I can once again try to see, is there a shape that captures this compatibility of tubes? Again, the single tubes would have to be edges of the shape, and then two tubes that are allowed to be together should correspond to vertices where the two edges meet each other. Okay, so can we do it? Well, it's it's a little bit cool, but if I draw this picture, indeed, I can do it, and it's captured by a pentagon. That's funny. It kind of looks like the Associahedron. Okay, so and indeed, if I take this, if I think this edge, for example, is let's say this edge is this tube, then I can make this edge can be this big one that's compatible with it. All right, so that would make this vertex would correspond to these two tubes that are allowed to occur together. And okay, and off we go. So so if we do the next one here, that could be this middle one. So this vertex here would be the diagram with this big guy and the middle one. And okay, let me just finish quickly. This could be the big guy on the other side, and this can be this destroyed one here. Okay, and so and I'll leave you to put in the rest of the vertices here. Okay, so is this clear? Again, we have an object on the right, which is capturing all of the combinatorics now of compatible tubes. Okay, ignoring the trivial ones that are there for all the graphs and are compatible with everyone. Okay, well that's very amusing. That the tubings here, the sort of geometry for the tubings are Associahedron again. Okay, so we see a point, an interval, a pentagon, exactly what we saw for the Associahedron. You can have fun working out that if you actually make just add one more to this chain, and now you look at all of the tubes, you'll get the three-dimensional Associahedron. Okay, but they're not always Associahedra. That's why these things are called generalized Associahedra. They're graph Associahedra. They're associated with the graphs. So let me just show you the next example. So already we did this example. Yeah, already we looked at this example that gave us a pentagon. Okay, but I can have another graph with 4 nodes that looks like this instead. Okay, remember this came from some 6-point diagram. This can also come from a different topology 6-point diagram. So sometimes we call it the Mercedes-Benz diagram. Okay, so okay, so let's look at what the sort of combinatorics is that's associated with this guy. Well, I have now, if I draw this picture, I can have tubes that look like this, and of course it's friends, and I can also have tubes that look like this. So you see already I have 6 kinds of tube, not 5 kinds of tube. Here, the clue that there was a pentagon is that there are actually 5 kinds of tube in this example. But here there's actually 6 kinds of tubes. And in fact, the picture that goes along with this is not a pentagon, but a hexagon. Okay, so let's, we can just see this example. Okay, so this picture, the geometry associated with this really looks like a hexagon. And again, I can think of this edge as being, let's say, that tube. The one on one side could be this way, this compatible tube with it. The one on the other side could be this compatible tube. Each vertex, for example, this vertex would be these 2 compatible tubes sort of on top of each other. So this complete tubing. And now the picture is cyclically symmetric, so you can just fill in the rest in exactly the same way. But so you see that this is now a different geometry, one that we had not seen before, 2-dimensional geometry we had not seen before in this setting. But in any case, there is a geometry that captures the combinatorics of how all the tubes come together. Okay, and these are called graph associahedra, and they exist in general. But in particular, we've discovered that the geometry that goes with the geometry that goes with these kind of graphs looks like a pentagon, and the geometry that goes with these kind of graphs looks like a hexagon. So I just want you to keep that in mind. Okay. All right. So now let's.
You have a question, Nima?
Yes.
Can I ask a quick question?
Yes, please.
In your previous slide where you had the 5-side chain, and you said that it looks like a 3D associahedron.
Yes.
Is there some assumption here about the fact that all of the tubings are independent?
Sorry?
Is there some assumption?
Here in this picture, we're only talking about the combinatorics of the tubings. We're not talking about what the variables are or anything like that. You're probably thinking about what you'd actually get with what you actually get when you think about the actual energies that show up in the tubes are the sums of the x's and y's. And so there are relations between them. So if we do that, there are sort of further relations between these variables. And so when you finally go and compute a canonical form, the canonical form for the final answer in terms of x's and it's your choice, by the way. I mean, you could just want an enriched object where you have a separate variable for every parameter. And from that bigger object, you're always free to specialize to the smaller one if you like. But if you want to get the answer for the final object where the energies are specialized, so there's relations between these parameters, relations between the tubes, then that indeed involves some contractions of the corresponding geometries. But that's at this point it's a detail, but it's very simple to see what those contractions what they look like, and to give explicit descriptions for the geometry, both for the case where all the variables are independent and in the case where the variables are, where the independent variables are directly the x's and the y's. But at the moment, I'm just talking about the I'm just talking about the pictures and nothing else.
Thanks.
Did that answer your question?
Yeah, that did. Thanks.
Any other questions?
So for these generalized associahedra, is there any hierarchy between them? That more complicated tree graph you have?
No, they're all, I mean, and all the nice properties of associahedra are true of these guys. They have Minkowski sums, they have everything. Everything that's true for ordinary associahedra is true for these guys.
Mm-hmm. Okay.
I mean, and there's explicit, you can cut them out with inequalities. Yes. So, but in fact, a way to cut them out with inequalities is going to be implicit in the story I'll tell you in a second for the Cosmological. But you can also, I mean, you can just have a lot of fun just staring at these graph associahedra by themselves without thinking about how they sit inside the larger Cosmological, which is what I'm coming to in a moment.
Any more questions?
Any other questions about this?
I think you can continue.
Okay. All right. So so now let's go ahead and try to think about what cosmohedra might be. So what is it that we're trying to do? Okay. Well, if we think about 4 points just for a second, this is 4 points is going to be a really too trivial example, because if I look at 4 points, I just have two diagrams anyway, right? You know, so I still have the S and the T channel diagrams, and okay, now I have to think about them in this sort of Russian doll way, but they're just 2 terms, 2 diagrams anyway, and so there isn't anything new. And one way of seeing that there isn't anything new is that for a single graph there is nothing new. A single graph, you know, there is nothing to do once we got rid of the trivial tubes. Okay, so so already, if you like, the sort of cosmohedron for n equals 4 just looks like an interval, just exactly looks like the same as the associahedron, because nothing new has happened. Okay. However, for n equals 5, already things are more interesting. So for n equals 5, already a single diagram, you know, so let's go and so we draw this thing. I'll draw it as a triangulation. I have this single diagram. This single diagram might look something like this. If I draw it as a diagram, it would look like this if I draw it as one of these graphs that we're talking about. But this single diagram already has 2 tubings associated with it. Okay, so we have this one. Sorry, I'm only drawing the not non-trivial ones. I have this one, and I have the other one, right? Right, and again, we drew it before, but that's sort of associated with the fact that I can have this square, or I can have the other square. I can have these 2 squares in this picture. Okay, so so we know what a single diagram wants to be. A single diagram wants to already be an interval, right? That's what we decided. A single diagram wants to already be an interval. Okay. On the other hand, if we think about what sort of glues all of the diagrams together, well, all the diagrams are grouped into a pentagon, right? That's the ordinary associahedron. So if we just imagine starting off with the ordinary associahedron, right, we want to start with the ordinary associahedron, then this vertex here in the ordinary associahedron, this is some triangulation or diagram, you know, however you want to think about it. But somehow, if we want to capture all the Russian dolls, we want to sort of zoom in on this vertex. And in that vertex, we don't want to see a vertex. We want to see what? We want to see this little one-dimensional geometry instead. So instead of seeing this vertex, we want to see that this vertex actually turns into something like this, right? Where on one end, I would have, on one end, I'd have one of the tubes. On the other end, I'd have another one of the tubes. Or if I drew it in the language of triangulations, right? On one end, I would want to have one of these squares, and on the other end, I want to have another one of these squares. Okay, and then together with the rest of them. Okay, together with the rest of the trivial ones that are just adding the total energy that's going to be there for everywhere and the little triangles. Okay. All right. So, well, in this case, it's sort of happily clear what to do, right? Because all I have to do is take this pentagon and turn it into a decagon, right? So I'm just going to literally do this. I'm going to just take every one of these edges and just and blow them up. Or another way of thinking about it is I can take the associahedron, which was this pentagon, and I can shave off these vertices. Okay, I can shave off the vertices and turn them precisely into these intervals. Okay. All right. Now let's look in a little bit more detail at what we're doing here in this Tengon. You see here, what I want to be turning. So let me draw it like this. So 6, 7, 8. Sorry, I'm drawing a very bad Tengon. Let me actually draw it like this. Okay, so we've already decided what we want these various. Okay, I think this is not going to work nicely in. Let me just try one more time. Do it like this. So this is the things that we sort of things that we've shaved off. But the point is that we can think about each one of these edges now. So if I think about this edge as so one of the old edges of the Associahedron was this. Okay. Now I think about every edge here as a partial triangulation. See, even this edge here is now going to be this full partial triangulation. That full triangulation, that full triangulation is labeling an edge now. It's not labeling a vertex like it was for the Associahedron, because it's labeling what that vertex got blown up into. It got blown up into an entire edge now. Okay. So the edges of this Tengon are actually are the edges of the Tengon, the codimension 1 boundaries, but in this case, the whole thing is just 2-dimensional. So the edges of this guy are labeled by partial triangulations. And now the further vertices, the vertices are now labeled by Russian dolls. Okay, so for example, this vertex here, who is this vertex? This vertex is at the common is at the meeting point of this partial triangulation and this partial triangulation that happens to be a full triangulation. Okay, so what do you get when you overlay these two guys on top of each other? Well, I now think about each one of these. I think about each one of the edges. On the one hand, I can think of it as a partial triangulation. So you give me a collection of non-overlapping chords, but that collection of non-overlapping chords also gives me a collection of non-overlapping subpolygons. Okay, so in this case, the non-overlapping subpolygons are just the complete triangles. In this case, it's this triangle and a square. And so what I'm supposed to label this vertex with is just put on top of each other the collection of non-overlapping subpolygons that are associated with the partial triangulations on each side. So that's how this vertex gets associated with a particular Russian doll, which is these triangles together with that from one side together with the square on the other side. Okay. So is that clear? So I just wanted you to get two things from the example. First, that in order to make a geometric, and so this is indeed it's a geometric object where every face of every dimensionality is associated with a pattern of non-overlapping subpolygons. The codimension 1 faces are just the subpolygons associated with partial triangulations, and then the higher dimension ones are just filling them in. Okay, just in just the way we saw. Okay, so I wanted you to see two things here. That one, that we could obtain this object by starting from the Associahedron and shaving something off of it, and two, that when we're done, object had faces that were facets, codimension 1 facets that were labeled with general partial triangulations, and then the vertices, or in this case, more generally as we go to lower dimensional faces, are now given by collections of non-overlapping sub-polygons. Okay. All right. So having seen that, let's now move on to the case of n equals 6. Okay. So if we do n equals 6, the idea is to start from this picture on the left. Okay. So we have the normal Associahedron here. Let me move this guy out of the way. Okay. But now let's remember what each one of these vertices corresponds to. So for example, that vertex here, this vertex there, it's associated with this. I'll just draw it again. It's associated with one of these diagrams. Okay, so that's the corresponding diagram, looks like that. So the corresponding graph, the corresponding sort of graph looks like that. And we already decided that its graph associahedron for this guy looks like a pentagon. Okay. And that's also the case for this guy and this guy. All of these things, their graphs look like this, and the graph associahedron looks like a pentagon. There's 2 examples that don't look like that, which are the sort of top and bottom of this picture. This top picture, okay, there is a triangulation. I'll draw it again. And the corresponding diagram is exactly the Mercedes-Benz guy. Okay, so its graph looks like this. And its graph associahedron is a hexagon. Okay, similarly for the guy down here, its graph associahedron is a hexagon. Okay, but you see again that there's reason for optimism here, because what we want to do is zoom in on every vertex here and blow it up into an object. But the sort of happy coincidence that makes everything work, of course, is not a coincidence, but just in our narrative here, the happy coincidence that makes everything work is that the full object is 3-dimensional, but what I want to blow the vertices up into, so you see each vertex now wants to be blown up into a graph association, which is 2-dimensional. That's exactly correct to be able to do it, to be able to like imagine taking this picture and blowing these guys up into pentagons, blowing this guy up into a hexagon, the vertex up to a hexagon. Of course, it's non-trivial. I have to be able to blow everything else up in between. This edge has got to get blown up into something. Okay, all of these facets, everything has got to change in some consistent way, but it has a chance just because of dimensionality. Okay, because the dimensionality of the graph associahedron that would go along with the vertex is always 1 less than the dimensionality of the full associahedron that the space lives in. So it's sort of possible to imagine blowing it up for this thing to actually work. All right. And it does work, of course. Okay, so that's the beautiful thing, and this is what the object looks like. Okay, so exactly as advertised, you see what we see on this picture on the right is this vertex here has turned into this pentagon. This vertex up here is turned into this hexagon. Okay. And you see this edge here, this edge has turned into this little rectangle. Okay. So we have indeed blown everything up. Now, what's drawn in this picture on the right, are only the, what I've filled in on the picture on the right are only the codimension 1, only the facets. And so you see the sort of cool thing which has happened is that every face of every dimensionality of the associahedron has turned into a facet, has turned into a codimension 1 facet of the cosmohedron. Okay, so this is the cosmohedron in this case. So you see this edge got turned into a face. This vertex got turned into a face. The thing that used to be a face before is a face again. Okay, but every one of these things got turned into a face. So the faces of the cosmohedron are labeled by, as I said before, partial triangulations, which in turn you can think of those partial triangulations as also giving you a sort of a non-nested collection non-overlapping subpolygons, only non-overlapping subpolygons and nothing else, no nesting. Okay, so that's what the facets look like. That's what the codimension 1 boundaries look like. Okay, but all the other faces of all dimensionality can be read off by seeing what you get when you overlay these things on top of each other, and that's what gives you the nested Russian doll structure. So that's what we see in this next picture. So this is zooming in on this part of the cosmohedron. So now we've labeled everything now. So but now they've been explicitly labeled in terms of non-overlapping subpolygons. Okay, so this face here, this face of the cosmohedron is labeled by this partial triangulation, which I can, this partial triangulation just with that one chord, which I can think of as breaking the hexagon into this sort of pentagon and the triangle, okay? But now this not face, this edge of the cosmohedron now involves this the nesting of these sets of subpolygons together until you get all the way down to the vertices of the cosmohedron that are full sets of non-overlapping subpolygons put on top of each other. Okay? So that's
Nima,
what the
can I
object
ask here? So
yes.
I know
Yes.
that the cosmohedron does it for you, but was it kind of obvious that the thing would glue together correctly on
Definitely
the lower
not.
dimension? That was
Definitely
not
not.
obvious.
Definitely not.
There
Definitely
could be
not.
twists and like
Oh,
overlaps and
absolutely.
things like
Absolutely.
that. Yeah.
No, it's very non-trivial that this exists. Definitely. I mean, it was already non-trivial the associahedron exists,
Right.
but yes, it's definitely not non-trivial that this object exists. Yes. Yeah. Yeah. Just from what I said is not. I mean, it just gives it a hope that you can shave things off and make it work. Okay?
But do you have some understanding why exactly it glues in this way? Why you don't have any twists, overlaps, like non-planarities?
Yes. So that's. I mean, it's not. It's not a total. It's not a complete. It's not a complete proof. But there is a way of motivating all of this, so it's sort of much more sort of transparent that something like this should happen. If you think in terms of the sort of dual fan picture for this for these polytopes rather than the polytope itself. So in the sort of fan picture, you have a vector that corresponds to every normal ray to every facet, and there are cones that are built that correspond to the facets that meet at a vertex. So so there's a sort of very well understood sort of nice cone for the sort of fan for the associahedron and for all generalization to all surfaces as well, to all orders in the topological expansion. And you can think of the cosmohedron as refining that fan in a very natural way. So, you know, if you take the associahedron and you have, maybe I'll draw this, yeah, maybe, yeah, I'll come back to say something about this maybe at the very, I just have a few more, since I'm over time, I just want to say a few more things, but I'll come back to this point and say something about it maybe in a few minutes. But the short answer is, the really short answer is that no, you really have to sort of understand it. It's not manifest ahead of time. It couldn't have had twists. It couldn't have been totally crazy. The fan makes it more palatable that something like this should be possible, but it definitely doesn't guarantee it. So, so I would say that only when you get the sort of full picture and you understand how to cut it out with inequalities and so on does it become more clear why it's possible. Any other questions? Yeah. Oh, sorry. Oh, sorry. I froze here. Can you hear me now? Frozen. Okay, so you guys can hear me okay now. Very good. All right. I think I can't hear them maybe. All right. Okay. So, all right. So let me just say just a few more things. I'm out of time, but I want to tell you what the sort of the combinatorial definition of this object and how to cut it out with inequality. Okay.
Can you share it, reshare your screen?
Oh, I'll reshare my screen. Yes, I certainly can. Just 1 second. Can you see the screen?
Yes.
Okay, great. All right. So let me just okay, so first, what is this what's the sort of combinatorial what's the combinatorial property, the defining properties? It's very, very simple. So the Associahedron is an object where the faces of any dimension are partial triangulations. Okay, so let's call them partial triangulations, or partial or collections of non-overlapping chords. Let me call it C, which is collections of non-overlapping chords. So literally a list of non-overlapping chords. Okay, and the idea is that a face F is F prime is a face of F. Okay, so F prime belongs to F if the collection that goes along with F is like literally a subset of the collection that goes along with F prime. Okay, I mean, that's just the statement that that the collection of chords for F prime is a refinement of the collection of chords for F. You just add more of them together. Okay, so that's what the Associahedron is. Okay, the Cosmohedron is exactly the same thing with the word chords replaced by subpolygons. Okay, so the Cosmohedron is an object that has a that has faces for collections of non-overlapping subpolygons. So let's call them P. There's a little rule here to be totally precise, which is that if you have a collection of subpolygons, so for example here, so let's say you have this. Here's a collection. You have a triangle. You have a triangle. You have this pentagon, and I also have this square. Okay. This looks like a legal collection of non-overlapping subpolygons. They don't overlap each other. But it's not allowed in our list. Our list has to have what the Russian doll property, which is that if a subpolygon is filled, so in this case, if this pentagon is filled with something, which in this case it does have a square inside it, then it must be completely covered. Okay, so I can't have this square without filling in the rest. So I also have to have this triangle that goes along with it. Okay, so it's a collection of subpolygons that are non-overlapping, literally a collection of, you just give me a list of subpolygons that are non-overlapping. But if a subpolygon has another subpolygon inside it, then all of it must be covered with some other guys as well. Okay, so that's it. So with that rule, the faces are associated with collections of non-overlapping subpolygons. And F prime is a face of F. Again, literally, if this collection P is a strict subset of the collection P prime. Okay, so it's exactly the same combinatorics with the word non-overlapping chords replaced with non-overlapping subpolygons. Okay, so that's the first statement. Similarly, we can cut out the Cosmohedron with inequalities. Okay, and so how do we cut it out with inequalities? Remember, for the Associahedron, we had our x's. We had the so for every chord ij, we had some x ij. I'll just drop the ij, and so we had inequalities that look like x bigger than 0 together with these ABHY conditions that look like this: x plus x minus x minus x equals some constant, where these constants were also bigger than 0. Okay, so that was the story for the Associahedron. Now, what we're going to do is going to take the Associahedron and just shave off. Okay, so that was what we saw we were doing geometrically. So shave off means that we're just going to add a bunch of inequalities. Now, remember, the facets these are what the codimension 1 boundaries are going to be. Is what the inequalities are going to be cutting out with the facets. The facets are associated with a collection of non-overlapping chords. And therefore, the most natural way to have some inequalities is if there's a bunch of chords, little c1, little c2, little cj, then I'm going to write down an inequality not on. So the Associahedron just says there's an x for each one of them. Says that x for cj should be positive together with the ABHY conditions, right? With the ABHY plane. But now we're gonna add some new inequalities, and the new inequalities are going to be associated with all these new facets, and they're just going to be that for any partial triangulation C. So for any partial triangulation C, I take the sum of all of the XCs for the chords in this triangulation. And I ask these should be greater than or equal to some epsilon that depends on this partial triangulation C. So for every C, for every collection of non-overlapping chords C, I take the sum of the X's for all the chords inside C, and I ask them to be bigger than some epsilon. Now I write this epsilon because I want to imagine that these epsilons are all much smaller than the C's of ABHY. That's because I want to imagine that I'm starting from the Associahedron and I'm shaving off something. So I'm not making a violent change to the structure of the full Associahedron. This is still sort of provisional. It should be possible to come up with a completely unified description of the whole thing where we don't make this distinction, this hierarchy between the Associahedron part and the shaving part. But at the moment, this is a simple thing that we can do. But these epsilon C's cannot be chosen randomly. This is now related to Yara's question of like, how do you make sure that you can sort of shave things off in such a way that you cut out the correct shape, okay? And the remarkable thing is that the epsilons have to be characterized in the following way. So how do I choose the epsilon? How do I choose the right-hand side for a given partial triangulation? Well, first, in this partial triangulation, there's a bunch of subpolygons that I see in the picture. With every subpolygon P that I see, I'm going to associate a parameter, I'll call it delta P, another small parameter. And epsilon C is going to be the sum over all the polygons that we see, all the subpolygons in this partial triangulations of the delta P's. Okay, so that is putting some hierarchies between the epsilons. Roughly speaking, this is making sure that you shave off vertices, then you shave off edges, then you shave off higher dimension things. That's the roughest way of saying it. But in fact, these deltas themselves have to satisfy a very interesting inequality. They have to satisfy that the delta for polygons P plus delta P prime should be less than or equal to the delta you'd get for P union P prime and the delta for P intersect P prime. Okay, so this is the really magic condition. So there are sort of two things going on. This is the answer to Yara's question ultimately. A, that when you shave off, you introduce new inequalities associated with these facets on the sum of the X's. That first of all, they have to be shaved in some way. You have to express the amount of shaving as a sum over some small parameters associated with the subpolygons, but that these have to satisfy these very famous relations. Now, physicists, mathematicians, everyone in the world has seen these relations. Physicists call them entropy relations, entropy cone relations. Mathematicians call them submodularity conditions. They're ubiquitous relations, but this is where all the magic comes from. Is that with this restriction on the inequalities, the way the Associahedron gets shaved off turns it into the Cosmohedron. Again, there's something remarkable going on here. Just like the Associahedron, we did not go in to the Associahedron asking to produce Feynman diagrams. We just have this picture of X's with these simple X plus X minus X minus X that you can motivate in various ways, but definitely nowhere did we say the word Feynman diagram. Similarly here, having done that, we just impose conditions on the sum of the x's associated with partial triangulations. They have to satisfy this interesting submodularity condition, and magically, what comes out of this is an object where all the faces are labeled by Russian dolls, and all the vertices in the end are all the sort of Russian dolls that contribute to the wave function. All right, so I think that's all I will say here. There's a number of other things that was done in the first paper sort of note on the subject. We talked about how you can actually extract the wave function from the canonical form of the cosmohedron, but this involves some novelties. It's not exactly the sort of classic way that you extract a physical observable from a canonical form. So trying to understand that better is an open problem. And one of the most fascinating open problems is to see, now that we have this object that kind of does the same magic for collecting all the Russian dolls for the wave function together, as the Associahedron does for the amplitude, is there any sense in which it's built out of simpler objects? Is there a Minkowski sum picture for the full cosmohedron? There definitely is for each graph Associahedron. That part is trivial. But that's already remarkable, but that's easy. Is there somehow an object that does the same thing for the whole thing? And that would be really fascinating because, in the case of the Associahedron, understanding that it was expressible as a sum of simpler pieces is the key to discovering sort of strings from the bottom up. Of course, in that case, strings existed for 50 years already. So that's Kobe and Nielsen could be very happy that you could rediscover their formulas in these fancy ways, but the formulas we've had for 50 years. We do not have those formulas for a stringy picture of either the cosmological or ADS wave functions today in any really practical way. It will be really fascinating if this picture gives us sort of another angle into seeing what such formulas might actually look like. And a final comment related to one of Suvrat's questions. Here we talked purely about the wave function, but you could also ask about the full correlators. This is something that sort of bothered me personally for a long time, thinking about amplitudes, is that we do all this work thinking about amplitudes, and maybe there's some whiz-bang mathematical structures that go along with them, blah, blah, blah. But in the end of the day, you have to mod square to get physical observables. And the mod squaring does not have a natural home yet in this universe of ideas, not an especially natural home. So it's kind of lame to go through all this song and dance to get these fancy schmancy geometric combinatorial blah, blah, blah structures to get an amplitude in the 21st century, and then mod square it because Max Born told you to do so in 1927. It would be much more satisfying if there was some intrinsic object that cares about the mod square to begin with. There's something better about the mod square. There's a reason to mod square, independent of the fact that Max Born said so in 1927. And so again, there's an opportunity to think about something like this here, because there's an enriched combinatorics, enriched Russian dolls plus something else that calculates the correlators. As we discussed in our paper with Carolina and Franciscu, there is a geometry for the full correlation functions as well. So we understand it even more poorly than we understand the cosmohedra, but the objects exist. And so that's one of the first indications I've seen for this sort of dream that we can have a raison d'etre for the mod square as well, not just for the amplitudes and the wave function. So anyway, I will close with this. I hope you got a sense from these lectures, A, of how elementary the ideas are here. They're maybe slightly unfamiliar from your quantum field theory classes or whatever, but they're very simple. They're things that would have been easy for people in the 1930s and 1940s on the one hand. On the other hand, there's it's kind of manifests the sense in which what I said in the very beginning, that it had to be that cosmology and the wave function and things like that gave us richer objects and amplitudes, just because the amplitudes lived on this sort of e-total singularity of the wave function. And in a very concrete sense, we are seeing that here. We see that the Associahedron, the amplitude magic doesn't go away. It just gets blown up into something even richer when we think about the wave function. Our understanding of these things is totally primitive right at the very, very start. And as I also said in the very beginning, this is a field that's much more driven by talent than by knowledge. So anyone who's sort of interested in jumping in and playing is sure to be able to make some exciting contribution if they just stick at it for a little while. So, okay, so with that, I will end and thank you very much. Sorry for going over time.
Thank you, Nima. Okay, we will thank Nima again for both lectures.
See you guys later.
Thank you, Nima, and